Okay, welcome back. Let's start looking at certain examples to better understand the effective number of hypotheses for certain situations. So the very first example that we're looking at is a one-dimensional positive ray. This hypothesis, like the one-dimensional positive ray, H, it comprises of, or it consists of all hypotheses of the form H of x equals the sine of x minus W0, which you can see here. So basically think of it as a straight line such that there is this threshold W0 and it's in a one-dimensional space, so that means it returns a -1 if it's to the left here, right? Red is consider it as -1 to the left of some value or some threshold W0. Let me write it down. This is my threshold, and it's a +1 if it's on the right-hand side of W0, right? So this is how this particular hypothesis can be defined. Okay, we are looking at a very generic case. This is different from what we did with the perceptron when we were looking at like 3 points versus 4 points, right? So now we are going all out and we are looking at like n points. Be very generic so that we can come up with some generic value. Now, if there are n points on the ray, then the dichotomy is decided by the placement of my threshold, right? So my threshold can be placed here. So this one, these are all red ones and these are all blue ones. So this is positive, this is negative. If my threshold is placed here, then these are like on the right hand side will be positive, on the left hand side will be negative, and so on. So essentially I can place my W's anywhere between these points, right? So basically what we are looking at is the placement of my threshold. Where can we put this W0? In n points, how many regions can you think, if I have like n points, how many regions can you think of where my threshold can be placed? You can begin thinking like in terms of like 2 points, 3 points, and so on. So you can easily tell just by looking at it that there are n+1 regions where this can be placed, right? So there are n+1 regions where I can place my W0. So therefore, the number of dichotomies, the maximum that can be implemented with this like n+1 points, in this situation, the ones that can be implemented, so that's all I care about, is mh of n, m sub h of n equals n+1. N could be any positive number, right? So this was an easier example. We could just by looking at it, we can tell that these are the number of dichotomies that can be implemented, and I can come up with an equation in terms of the number of points, which is n+1. Okay, so what happens, right? We are really interested in the effective number of hypotheses here, right? So what happens if, like, let's put that in a tabular form, and that would make things easier for us. For this particular example, what happens if my number of points is 1? Can I implement all possible dichotomies or all possible based on like my given hypotheses? Can I do that? Let's look at it, right? So 1, 2, 3, 4, and so on. My points will go on increasing, and my m sub n, let's see. So if I had just 1 point, right, how many number of effective number of hypotheses or the number of dichotomies, that's a better way to put, can be implemented? So this is going to be n+1, right? So this is 2, right? With 2, because we have come up like with the formula for m sub h of n. So if there is any confusion, basically I'm trying to just implement this formula here, right? So here with 2, it is going to be 3, right? Now, even before moving forward, what did we say in general about the number of dichotomies that can be implemented given n data points? Now, the worst case scenario that we looked at some time ago was 2 to the n, right? So according to this worst case, this here, like let's also calculate 2 to the n along with the m sub h of n, right? So 2 to the n here, 2 to the 1 is 2, and this is 4, right? But the number of dichotomies that can actually be implemented is 3. So 3 is strictly less than 4 already, right? And the number of dichotomies that can be implemented by 3 points is 4, because 4 regions, n+1. and this is 8, right? And similarly 5, 16. So why am I like making it in a tabular form is to show you that there is this deficiency that has started to occur, just like for this particular hypothesis set, just at n equals 2. When I came up with 2 data points, I can see that the actual dichotomies that can be implemented are less than the worst case that we came up with, which was 4, right? What this is telling us is that there is hope, right? Because we see that out of the infinite hypotheses that we can have, obviously, right, there are some finite number that can be implemented. And that finite number starts to get lower as we increase these endpoints for certain cases, right? And it's less than the worst case that we were expecting for that particular end. Another way of saying this is that if you think about this like particular hypothesis set, what has happened at point number 2 is that the hypothesis got broken. Sometimes you also say that because of the deficiency it has created, right? But got broken at n equals 2. This is what it tells us, right? There is no need to go beyond that because it breaks at that point, and it's less than the 2 to the n that we were sort of thinking that we need to implement. Now, we can come up with a similar, like a tabular form for a perceptron, and let's see where the perceptron begins to break, right? And obviously we did that like manually, so from our earlier analysis, I'm just like putting that here in a tabular form to put things in perspective, right? So as we increase the number of points, if you remember m h of n, the number of dichotomies that could be implemented with one, like both. And what is 2 to the n? 2 to the n, because n is 1, it will be 2. And then we saw, yeah, with 2 points, yes, all of them were implemented. So that was also true. With 3 points also, there was this scenario where we could implement. So the worst case was still 8, right? And so calculated value 2 to the n is also 8. But there was that one scenario, there was that one situation where we saw that like this 4, when we come up with 4 points, right? We saw that we cannot implement that alternate hypothesis, alternate dichotomy with my perceptron model, right? And so the maximum number possible, 2 to the n, which is 2 to the 4, is 16. And so here 14 was less than 16, right? So basically we can say that this perceptron is broken at n equals 4. Right? We can go ahead and compute it for 5. In fact, it's a combinatorial problem, and I'm leaving it to you to try and understand how that can be done. But this break point is the one that's important to us, right? This is important to us because we can tell that we don't have to starting from n equals 4 only, we don't have to look at every possible hypothesis coming out of the perceptron model. And as I said earlier, this gives us hope. This gives us this idea that, yes, the effective number of hypotheses is less than all the hypotheses that were possible under a hypothesis set. Okay, one more example quickly to better understand this, and that example is positive rectangles. So what are positive rectangles? If this is the x and y plane, and if we have an axis aligned rectangle, for example, let's say this is aligned with this, so parallel to the y and parallel to x somewhere. It could be anywhere in this space essentially, but has to be like parallel. So what we are thinking about this hypothesis set is that anything inside here will be considered positive and anything outside will be considered negative. Anything outside is negative, whatever comes inside is positive, right? And in order to demonstrate what's going on here, let's look at some points, right? So in this space again, if let's say I have like 4 points, let me have 4 points, any way is okay, right? And let us assume the alternate one, because remember the alternate one always creates some kind of, you know, deficiency. So let's begin with the alternate one is all I'm saying, right? And what I have to do is like basically come up with a rectangle that could classify positive and negative, right? So anything that comes inside that rectangle is going to be a positive, anything outside is going to be a negative. That's all I'm considering here. So for this case, all dichotomies essentially can be implemented, right? So if you think about this particular case, I can come up with this rectangle. So no matter what the alignment of these 4 points is, you can go and check yourself. we can implement all possible dichotomies, alternate or not alternate. We can implement all of them. So for this particular situation, we can say the maximum number of dichotomies that can be implemented with 4 points under this hypothesis. So that's why we write it like m sub h of n, which in this case is m sub h of 4, is 16, which is 2 to the n. So in this case, yeah, for 4 points, this is not deficient. It's not broken for 4 points, right? This positive rectangles hypothesis. So this is kind of telling us that this theory that we are coming up with, that this hypothesis becomes deficient for a certain number of points, is also dependent on the hypotheses that you're using to categorize your data, right? In this case, my mh of n at 4 points is not broken, right? We can implement all 16 dichotomies. Now, let's consider further about, like, let's think more about this positive rectangles hypothesis. Let me draw it on another page. And instead of 4 points, let's consider 5 points, and any 5 points. So let's say these were my original 4 points. Let me add one more here, such that I have like some kind of an alternate, right? We seem to like alternate a lot because alternates create some kind of, okay, let me create a slightly more complex one. Okay, can we implement this using a rectangle, positive rectangle hypothesis? Can we do that? Well, if you think about this, right, if I'm trying to create a rectangle like this, and like trying to accommodate positive, like the positive values within the rectangle, there is no way I can avoid this point here, right? So in this situation with 5 points, I can definitely show a number of combinations in which I'm not able to implement this, like all possible dichotomies essentially. So I can say that this hypothesis is broken at 5, which means that m sub h5, where h is this positive rectangle, is less than 2 to the 5, right? So basically, what did we prove here? So what we proved is that with 5 points, there is always a dichotomy that cannot be implemented. Obviously, I don't know the exact value in this case. Maybe I can go and find out. But the point is that at 5, my hypothesis is going to be broken, right? So basically, I don't need to, like, I cannot, right? I cannot implement all possible 2 to the 5 dichotomies here. Okay, so these were the 3 examples that we wanted to look at. Let's summarize all of that here. So as you can see, what's happening, these are the different hypothesis sets. And initially we started an analysis saying that the worst case, like the worst case possibility for all possible hypotheses in every set is 2 to the n. And we figured that that's not a very useful number for us, given n could be anything. And it wasn't really helping us in the error bar, if you remember, right? So we began analyzing this further through the lens of the data, right? So now through the lens of the data, we found out that it's really not possible to implement all possible hypotheses, but rather there is this effective number of hypotheses that we will be implementing, right? So there is this effective number, and that depends on my h, my hypothesis set, and my n, right? So in this 2-dimensional perceptron, we saw that, like, as n increased at 4, we found out that there were two situations which could not be implemented. So like my hypothesis was set to break, right, at that n, and that n is now termed as a breakpoint. This is known as a breakpoint. So for any n, like if I have like m sub h of n, which is strictly less than 2 to the n, then I know that my hypothesis has been broken at n. So for example, here, my hypothesis has been broken at n equals 4. Similar to that, for the positive one-dimensional positive ray, my hypothesis was broken at n equals 2 because it started to become deficient at that point. And for the 2-dimensional positive rectangles, it broke at 0.5 because at 0.5 we realized that we cannot implement all possible scenarios or all possible cases, right? So the basic idea here is that m sub h of n, which is the effective number of hypotheses, drops below 2 to the n, which means there is hope for the generalization bound. So this is the key idea. This is all we were after, that this is what we were trying to get at. We cannot realize all hypotheses from an infinite set given a data set. And when we like illustrate that deficiency, then that is the breakpoint for that hypothesis set. And that helps us like drop the value for this m sub h of n below 2 to the n. And that is good for the generalization bound, which, if you remember, is the Hovding's inequality, right? And so the key takeaway from this part of the lecture is that infinite hypothesis sets, they do not reveal the full potential of diversity when viewed in terms of the data. What I mean by diversity is like that, like we cannot all the time, in most of the situations, we cannot implement this 2 to the n given the data that we are dealing with. That's like the first key takeaway. The second key takeaway is that there exists a breakpoint. So again, I'm emphasizing that becomes obviously challenging to compute in certain situations, but it's always good to have a formula to find the upper bound for effective complexity. For example, in this case, we found an upper bound, right? I couldn't really come up with a formula for m sub h of n, but I knew that there is an upper bound, there is a breakpoint, and that's what we're trying to get at. We won't be able to compute the exact value all the time, but we can definitely be able to find what is that breakpoint until where we should be searching and go forward from there. Okay, so with this, I'll end this video. In the next video, we'll look at a combinatorial puzzle, which is going to help us move forward with other parts of the course. Thank you.